good afternoon or good evening, depending on where you are. The topic of this workshop is the use of a particular kind of AI algorithm, which is known in the industry as autoregression. It has a variety of algorithms from which one can pick and work around with. There's Pixel CNN, there's Pixel CNN++, there's gated Pixel CNN, there's Pixel Snail, and I'll talk about all of those through the course of the workshop and the subtle differences between the four and which probably works faster compared to the other. The workshop is titled, or the workflow is titled DeepIsomer, because we're going to take a 3D and develop variations of it, which is very similar to what isomers are in chemistry, where the constituent structure remains the same, but the pattern in which the composition is connected to each other varies from one to the other. For example, carbon in its pure state versus carbon as diamonds. The fundamental makeup is the same, however, the structure is different. And we're going to go through those and how AI can be used to iterate 3D aggregates or 3D forms without us having to go through the process of explicitly defining what rules or the logic of the 3D is, which we tend to do when we work on Grasshopper, right? So we tend to explicitly mention the rules and then we iterate. We won't need to do that. However, because this process, this workflow is fresh out of the oven, of course, there are limitations, and with time, the limitations will be met with smart solutions, and I will, of course, demonstrate the limitations as well. I need to apologize for missing out on yesterday's session. There was an emergency, and I had to relocate my stuff to this room. As I mentioned in the email, I'm going to redistribute the content of the workshop across these 4 days. So the way we're going to work is that today I'm going to introduce the concept of AI as a whole, as to how it is placed with regard to the practice or the profession of architecture. And then we are going to work on hands-on on using DeepIsomer to iterate through two-dimensional voxels, which is the easiest form of iteration. But keep in mind, we are not going to explicitly define the rules of the composition. The AI algorithm will take care of deciphering the rules of the composition and then iterating it. And tomorrow we are going to work with three-dimensional voxels, where the distribution of voxels will vary in the z-axis as well. And the last 2 days, we are going to work with absolute regular three-dimensional models, which have no correlationship with voxels. It's designed in this manner to sort of take you through progressively from, let's say, the easiest task or easiest example to the most complex task or the most complex example. I'll briefly talk about how AI sort of seeped into the business of architecture. This image that you see is of two gentlemen playing the game of chess. The one on the left is one of the grandmasters at the time, Garry Kasparov. He is not, in fact, playing against the gentleman on the right in the black suit. He is, in fact, playing against the computer in the background, which was developed by IBM at the time, called blue, and the machine was in a way designed to play chess against the best of the players. And this was in the year 1997, and this was in fact the first time that a machine had indeed defeated someone of the caliber of a grandmaster in the game of chess, which in a way sort of started pop socio-cultural declaration and deliberation and media publication on the idea of man versus machine, where people started to speculate that probably machines have become smarter than humans. However, the point to take note was that at that time, neural networks existed only as concepts. Computers had not developed enough to execute neural network. So in a way, the machine Deep Blue developed by IBM was not smart, so to speak. In 1997, the computational power of computers had increased to such an extent that Deep Blue utilized simple brute force to go through all possible moves given the condition of the state of the board, and then picked the move which would be the most appropriate for winning the game. It had no capability of pattern recognition. It had no capability of foreseeing moves. It simply used at each step, it simply used a brute search algorithm to go through all possible steps and picked one which worked the best. But at that time, this was considered AI, because at that time, this was the best that computer scientists could come up with, right? So even the definition of AI changes from one decade to the other. It's like a moving umbrella term. In the 1990s, the use of genetic algorithm, which probably a few of us have used in the form of Galapagos and Grasshopper, even that was considered a part of the state-of-the-art AI. However, now it's no longer considered a part of immediate state-of-the-art AI. So even the definition of AI or the algorithms which are considered as part of AI change from one time period to the other. Now, fast forward around 20 years, and this was a game between, first of all, this game is called Go, G-O, and this particular series of games was played between the then champion, or one of the champions, Lee Sedol, and AlphaGo, which was an AI algorithm backed with complicated neural networks, which was developed or rather backed financially by Google's DeepMind. Now, the thing to consider is that in the game of Go, and please, I can't emphasize enough on the statistic that I'm going to quote at the moment. The game of Go is significant for us because the number of ways or the number of move sets that are possible in a game of Go, just by the sheer arrangement of the pebbles that you see on the board, the number of those arrangements is greater than the number of atoms in the known observable universe. It's a staggering metaphor. The number of atoms in the observable universe is less than the number of move sets or arrangements possible in the game of Go, which means that even though the computational power had substantially become better and faster by this time compared to 1997 when the game of chess happened, they had not become fast enough or efficient enough to use brute force to go through those many possibilities each time Lee Sedol played a move, right? You can't possibly compute number of arrangements higher in number than the number of atoms present in our universe, right? So this is when Google developed AlphaGo, which was the first machine learning algorithm to defeat a world champion. It was trained to mimic human play by attempting to match the moves that the expert players had played earlier. Google DeepMind, or rather the AI, which is known as AlphaGo. AlphaGo was shown around 30 million moves, all in videos of expert players playing against each other. And it was trained to pick patterns of play and then save different weightages as to which pattern of play is more suitable in which situation. And by statistically going through 30 million moves again and again and again, it sort of went to a position where it could take on Lee Sedol. And because the machine did not start with the bias of us humans, right? So typically when a kid starts to play a particular game, the kid is passed on the bias of the coach or the trainer, that these are the kind of move sets, or these are the ways in which you're supposed to move on a field or on a board. Because the system or the machine did not have those biases, it sort of could detect patterns which were undetectable to the human mind. And so it ended up playing certain move sets, which eventually not only defeated Lee Sedol, but kind of astonished him, wherein at the end he ended up saying that the move AlphaGo had played was not a human move, and he had never seen a human play that move, and he found that particular move to be beautiful. Now, fast track couple of years more, Google developed another version called AlphaGo. This time, it was not trained on videos of join. No. I hope the screen is visible. If one of you.
Yes.
Right, great. Did I get disconnected in between? I'm not sure. I somehow got some sort of message or alert pop-up.
About 2 or 3 seconds, it's interrupted for me.
Yeah, same here.
Right, so I don't suppose I don't need to repeat anything substantial, I guess. Right, so as I was saying, after AlphaGo, Google developed AlphaGo 0, which was not trained on videos of humans playing against humans. Instead, it was taught the rules of the game, or in other words, the rules of the game was coded into the system, and it started playing against each other. And at that speed, it ended up playing, I think, around over 1 billion games against itself in just 3 days of training. And just at the end of 3 days of training, it went toe-to-toe with the initial version of AlphaGo, which had learned its weightages, neural network weightages, from watching human videos. And just in 3 days of training, it defeated AlphaGo 100 to 0. So you can sort of guess the speed at which these algorithms are being developed, and the paradigm shift when a system is made to play against itself versus when a system is made to train from pre-existing human playing pattern. The challenge in training through videos is that the amount of data is finite. You only have X minutes of video of humans playing against each other, right? However, if you make the system play against itself, potentially there could be infinite number of games that it could play against itself. Now, so we've seen, we know about the existence of AI and machine learning in almost everything around us, right? So from self-driving cars to classification problems when Netflix or Amazon suggests us similar products, to music recommendation in Spotify, also predictive text in mobile. So when we start typing a word, depending on the previous words and depending on the alphabets typed in that particular word, our mobile tells us gives us few alternatives from which we can pick. And all of these are personalized, right? But there's a caveat to it that if we have to draw parallel to the speed of development of parametric tools, then it sort of doesn't paint a good picture. In the early 1990s, Frank Gehry was at the helm of designs of the Barcelona Fish, of the Guggenheim Museum in Bilbao. And as you must know, at that time, the predominant tools used by architects were not capable enough to handle complex geometries. And even if one could model complex geometries, forget about rationalizing them and then automating drawing production, which is one of the key tenets of parametric design tools, right? So it's not just exploration of design, but it's also got as much to do with automating drawing generation. So he ended up hiring a guy named Rick Smith, who was an expert of the software named CATIA, C-A-T-I-A, which was at the time being used predominantly by the automobile industry and the aerospace industry. Why? Because, of course, automobiles and airplanes have double curved surfaces, so they had software which could deal with that. Frank Gehry's practice was one that he could afford to hire such an expert. And of course, the rest is history, as in Barcelona Fish was constructed, Guggenheim Museum was constructed, and he sort of went on to achieve immortal fame, so to speak. But the caveat is that while this happened in the early 1990s, it took us almost 15 years to have the first installment of Revit, and almost close to 2 decades for Grasshopper to be released. So starting from a point where a particular practice hired a particular expert to work on 2 particular projects, to a point where those tools and tricks and techniques were presented to the profession at a much wider scale with a more automated solution without custom code snippets being written, which could only be controlled by an expert like Rick Smith at the time. Probably not only, but one of the few. So it took a lot of time, which is in a way alarming, because right now the business of AI and machine learning in architecture and design industry is in this Frank Gehry stage. And one can only hope that we reach the Revit Grasshopper stage much sooner than the 15 odd years that it took at the time. And so in a way, we are at a watershed moment. But keep in mind that most of the work that you will see in this domain of AI in design is rather speculative in nature. There are only a few direct applications that could be taken into a design workflow. A lot of the direct applications are in the analysis of design or analysis of space, and I'll give you a few examples of those. Now, one may ask or wonder that, you know what, chess has been gamified, and in fact, chess is a game. The chess has been represented in AI and it has been solved. Go has been represented in AI and it has been solved. Why can't we have at least arrangement of spaces, if not interior layout? Why can't we have that addressed by AI? The fundamental problem is in the number of arrangements that are possible. So if you look at the lower row of this particular slide, you can clearly see the significant jump in the number of arrangements that would be possible if we go towards sort of large scale buildings, which could be a campus building or a hospital or a hotel, where you go beyond 10 or 20 rooms and the number of possibilities increases to such an extent that even if Google decided to address the problem today, it would find it more difficult to address it compared to developing the AI to play the game of Go. And the other reality is that architects are still sort of borrowing ideas from computer science. Probably when we'll have one of the research labs invest enough amount of finance and work hours into investigating this, we'll probably have this solution. But my opinion is that we are still a good 5, or realistically speaking, 10 years away from achieving this state. Now, if I have to give you an example, right, so most of the examples, and the two examples that we sort of discussed till now were quantifiable. They were games, or the algorithms were solving discrete states with a given end goal, right? And which is why at that state, not a lot of AI research was being adopted in the domain of design and architecture, because most of the problems or examples that we saw problems being solved were either gamification problems or problems to do with hardcore quantification, such as using machine learning to predict the price of real estate given the historical trend of real estate, right? So examples pretty similar to stock market prediction or price fluctuation. But all of that changed in the year 2018 when Christie's, one of the most famous auction houses of the world, I think they were at the time based in New York and London. If I'm not wrong, they have closed down after they sort of had a fake painting scandal, I think a year or two back. But at the time, they were the most well-known art auction house, and they sold this particular painting, which was sold for almost as high as $500,000. This particular painting is known as the Portrait of Edmund de Bellamy, but this is significant because this portrait was not painted by a human. An AI algorithm was trained with 15,000 portraits from the 14th century to the 20th century. And the AI algorithm was trained to produce images which were different enough from the initial images or the training images, but similar enough to be not considered completely abstract. So they were sort of in between, where they were not as close to them to be called a fake painting, yet they were far away from them to be considered new. And at the same time, they were not far away enough to be considered completely abstract. So a very delicate balancing act that the computer scientists had to undertake. And this sort of became a watershed moment for the design industry, because this wholesomely demonstrated that even qualitative deliberations or investigations can be carried on in the domain of AI and machine learning. Just give me a second. I think someone wants to join us. Yeah. Which leads us to the first set of qualitative examples that were explored in the domain of AI in architecture, which was called, or is still called, style transfer, where the trained AI algorithm takes the style of a painting or an input image, for example, this painting of an Italian town, and maps the style, which is basically color, texture, which in other words means the brush strokes, onto a content image. Now, content in simple terms could be understood as the geometry onto which this style is to be mapped on, and we sort of get output like this. These techniques can also be sort of used on plans to interbreed plans of different styles. For example, you can see this is circular, this is rather orthogonal, and then you combine the two. The circular plan not only gets pixelated locally, but as if it is mimicking these long walls, freestanding walls of the orthogonal plan, that has introduced those as an extension and in alignment to the pixelated circular walls in this output. And of course, one can go through a variety of experiments with this, where if you vary the style image, the algorithm in a way automatically picks up the signature element. So we've already seen this, where it gets pixelated and then we have these freestanding walls being projected outside. In the case of a Palladian villa, the algorithm automatically picks up the characteristic, the visual unique character of the plan, which is probably the staircases, and it sort of populates them around this plan. Now, if 5 humans are asked to sort of copy paste the stairs around this particular plan, I don't suppose the output would be significantly different from one of these iterations, right? And in this case on the left, it has picked up the thick oblong walls of the chapel and sort of edited the circular walls in that fashion. So it's the fact that the machine can pick up these signature elements on its own is both beautiful and startling at the same time. Beautiful because the output is surprising in many cases, and startling because, of course, we didn't pinpoint the visual trait that it has to pick up, right? It sort of does that on its own. And of course, any slight variation in content will also generate different kinds of output. And these are just certain examples, and they work across various scales, from concept drawings to plans to even in the scale of urban speculation, where we have Knowledge Vienna map, which is a very good example of black and white figure ground relationship diagram, and on which the style map of, well, Vienna itself was projected, and you can see the output. So you can start having quick deliberations over what this means. And I also ran a social experiment with this, wherein I took a random painting, I projected it onto an Indian city. I am from India, and I projected it onto an Indian city. And this was the output on the right, and I uploaded it on social media. And as you can see from the kind of comments I got, people were kind of, in a way, fooled, which is unethical to a certain extent, but it's also proof of concept of the fact that unless people are explicitly told that a machine generated this figure, at least to the non-experts, it would seem like something that a human has indeed painted. So danger as well as potential go hand in hand. And of course, when we go deeper into the idea of AI, we also have to think about computation power, equity, and the authorship of the result, in the sense that since solving complex AI problem would need a high amount of computational power, will delivering such solutions be restricted to large organizations or institutes who will have the financial capability of accessing that computational power? So will we sort of no longer have individuals who will pop up with great examples, and with due course of time, will it be sort of be restricted to the established power chambers of the architectural professions landscape? And the second is, of course, authorship, wherein if someone is using images scraped of Google or Flickr or Google Maps or Twitter, and then even if it is under CC license, who becomes the author of the product? Because I am not explicitly making it. Is the authorship between me and the algorithm, or is the authorship between me and the algorithm and the owners of all the images that I had scraped and then subsequently used? These are questions which we need to answer, questions whose answers we still don't have at the moment. And probably we would sort of have a clear idea of these as and when we have more deliberations about it. I'll give you two more examples, and then I will conclude the introductory presentation, and we'll sort of have a 5-minute break. One of the exercises that we did in our practice was to use AI to quantify the difference between architects and non-architects perspective of originality in design. And why did we do that? Because we came across a lot of studies which concluded that, let's say, for example, buildings constructed with the elite code of design principles of architects, those buildings are unlikely to receive popular acclaim. And these are pretty well received research papers. And also, we also ran into another conclusion which said that architects in general cannot predict the public's aesthetic evaluations of architecture, which is not surprising, I would say, because we know that in a lot of the cases, architects tend to like brutalist architecture, exposed concrete, whereas in many of those cases, people around that area do not tend to like those designs, right? Anyway, so what we did was we took up the design of this particular building called Absolute Tower, designed by MAD Architects. I think it's constructed in Canada. I can't quite recall the city. If I'm not wrong, it is in the outskirts of Toronto, but I could be wrong about the city. We made a parametric representation of the star, wherein we also incorporated more parameters beyond rotation of star. We incorporated how the plan could change from an ellipse to a star-shaped plan to a complete box at times. And we also used a Boolean control for balcony where it could be switched on and off. And we basically got a bunch of them rated by both architects and non-architects in terms of how they perceive the originality of the design options compared to this original design, right? So if you look at this image, the one on the left is the original design, and these are few examples of the iterations that were, or variants that were rated, arranged in the order of originality, which is shown in green. And we sort of reached at certain very interesting results where we saw that architects tend to be more bothered about amount of rotation compared to non-architects. For non-architects, once we have rotation in a building, they sort of classify it as a twisting tower. They don't care if the amount of rotation goes from 150 degrees to 210 degrees. For them, both are rotated buildings, and they sort of think of them as the same. The other interesting fact was that for both architects and non-architects, presence or absence of balcony had similar impact, which could be used to conclude that when we are comparing the outer silhouette of a tower or a shape, then the local micro differences are ignored in equal measures by both architects and non-architects. Now, we then took the list of the values of the 12 variables and the average originality scores by both architects and non-architects, tabulated separately. We trained a neural network so that it could predict the originality perception by architects as well as non-architects. We sort of simulated it for 15,000 solutions. And why is the use of neural network important in this context? Because of course, we can't have 15,000 or 150, 100 options being manually reviewed by, let's say, the subjects of the study, right? So in a way, the 250 design variants that we got tabulated conceptually is represented by, let's say, these magenta dots. And then once these are rated and quantified, a neural network is capable of appropriating the solution space, which covers all the extents of all the variables. And once the neural network is trained, then we can sort of add or find out the performance, which in this case is the perception of originality of solutions which lie in between. And these are some of the outputs. As you can see from, let's say, the second last row over here, it's pretty evident that the options are greener for architects. More green would mean that it's seen as more original. And if you look at the histogram distribution, it becomes pretty clear that architects tend to see design variants as more original. quite counterintuitive to what I would have guessed, but it is what it is. Data doesn't lie. And to sort of summarize, the originality score of architects was on average 16.4% higher than the originality score by non-architects. Non-architects are likely to see a design as a copy or a plagiarized version by 1.7 times compared to architects. And architects, on the other hand, are on average tend to see a design as original 1.97 times more than non-architects. And in as many as 92% of the 15,000 simulated design variants through the trained neural networks, architects' originality score was found to be higher than the originality score of non-architects.